The moment you strap on a virtual reality headset, your brain immediately stops trusting your physical eyes and begins completely recalculating what it means to exist in space. You are not just looking at a screen wrapped around your face, you are actively forcing your nervous system to negotiate a brand new treaty between your inner ear and your visual cortex. Within 30 seconds of entering a virtual world, the physical architecture of your spatial memory begins to shift. This is not a simulation of experience. For your biology, it is the creation of a parallel reality. To understand what is happening right now inside your skull, we have to look at a profound biological mechanism called sensory-visual vestibular conflict. Your brain is a master cartographer, constantly updating an internal map of where you are using two primary streams of data. The first stream is your visual field, which tells you how fast objects are moving past your eyes. The second stream comes from your vestibular system, the fluid-filled canals inside your inner ear, that act like a biological spirit level, registering gravity, acceleration, and balance. Under normal circumstances, these two streams are in perfect, beautiful harmony. But when you put on a virtual reality display, that harmony is instantly shattered. Your eyes register that you are soaring over a mountain peak or turning a sharp corner in a futuristic vehicle. Yet, the fluid in your inner ear remains completely, stubbornly still. This discrepancy is not just a minor computing error, it is a biological emergency. Have you ever wondered why you get dizzy or nauseous when the virtual world moves but you do not? Your brain, in its evolutionary wisdom, interprets this sudden sensory mismatch as a sign of poisoning. It assumes you must have ingested something toxic that is disrupting your sensory integration, and it triggers the defense mechanisms of motion sickness to protect you. But the real magic is not how your brain resists the virtual world. It is how incredibly fast it adapts to it. To see this adaptation in action, we have to look at a groundbreaking study led by Dr. Mayank Mehta at the University of California, Los Angeles, in the year 2014. Dr. Mehta and his team of neurophysicists wanted to know how individual brain cells behave when we navigate virtual space compared to physical space. They focused their research on the hippocampus, the seahorse-shaped structure deep within the temporal lobe that serves as your brain's internal global positioning system. Within the hippocampus live specialized neurons called place cells, which fire specifically when you are in a particular physical location, creating a map of your environment. What they discovered was absolutely mind-blowing. When subjects navigated a virtual environment, the normal, synchronized firing patterns of these hippocampal neurons completely broke down. In fact, 60% of the place cells in the hippocampus simply shut down. They went dark. The brain's internal map of physical space literally collapsed because it was missing the physical, somatic feedback of real-world movement, like the feeling of wind on the skin, the changing resistance of the floor, and the microscopic muscular adjustments we make with every step. But here is the twist. Even though more than half of the mapping system went offline, the subjects could still navigate the virtual world perfectly fine. How is that possible? The brain was compensating by relying almost entirely on visual cues, rapidly rewriting its neural processing algorithms on the fly to build a temporary, highly efficient, and purely visual map of space. This is neural plasticity happening in real time. Your brain is not a static machine. It is a dynamic organ that will physically reorganize its processing power to match whatever reality you present to it. Your brain is rewriting itself. Think about what this means for your daily digital life. When you take off a virtual reality headset, the transition back to physical reality is not like turning off a television. Have you ever taken off a headset and felt like your own real hands did not quite belong to you? That strange, slightly unsettling sensation is not in your imagination. It is a documented neurological phenomenon known as post-virtual reality perceptual drift. Because your brain had to recalibrate its sensory relationships to keep you stable in the virtual world, it takes time to unlearn those adjustments when you return to the physical room. For several minutes or even hours, your brain is still operating under the assumption that visual movement does not require physical acceleration. Your motor control system is literally lagging behind physical reality. This brings us to a remarkable study from the year 2020 by cognitive scientist Dr. Mar Gonzalez Franco. She investigated the phenomenon of phantom touch and the ways virtual avatars alter our somatosensory cortex, which is the brain region responsible for processing the physical sensations of touch, temperature, and pain across our body. In her experiments, subjects wore virtual reality headsets and looked down to see a highly realistic virtual body representing themselves. When a virtual object touched their virtual skin, something extraordinary happened in their brain scans. Even though no physical object was touching their actual skin, the somatosensory cortex fired in the exact areas corresponding to the body parts being touched in the virtual world. Your brain does not actually know you are standing in your living room, it only knows the electric pulses arriving from your sensory nerves. When the visual evidence of touch is strong enough, the brain will literally manufacture the physical sensation to resolve the cognitive conflict. This is known as the Proteus effect. Your brain begins to adapt its very self-image, its neural representation of the body, to match the digital avatar you are controlling. If your virtual avatar has longer arms, your brain will temporarily alter its motor planning to calculate reaching distances based on those longer digital limbs. It is a level of biological flexibility that sounds like science fiction, yet it is happening every time you step into these immersive digital environments. This neural plasticity is a double-edged sword. On one hand, it shows that we can use virtual environments to accelerate learning, treat chronic pain, and rehabilitate motor skills after neurological injuries. By placing a patient in a virtual environment where their movements are amplified or assisted, we can trick the brain into reforming broken neural pathways much faster than traditional physical therapy allows. On the other hand, it means that spending hours inside poorly calibrated, low-latency virtual environments can lead to cumulative fatigue, spatial disorientation, and a subtle detachment from your physical embodiment. Let this sink in for a moment. We are now building digital spaces that are more visually stimulating than the physical world, but they lack the rich, multisensory feedback that our bodies have evolved over millions of years to expect. When you spend hours navigating a space where you can fly, teleport, or move without effort, you are training your brain to decouple action from physical consequence. Your brain is a highly efficient prediction engine, and if you feed it virtual inputs, it will optimize itself for virtual outputs. So, how do we navigate this fascinating frontier without losing our biological grounding? How do we harness the incredible cognitive benefits of virtual reality while protecting our physical neural architecture? The key is not to avoid the technology, but to actively manage the sensory transition zones. We can do this through 3 highly specific, scientifically grounded digital habits. First, you can implement what I call the tactile anchor protocol. Before you put on a virtual reality headset, place a highly textured, physical rug or mat in the center of your play area. Ensure that this mat feels distinctly different from the rest of the floor in your room. By keeping your physical feet on this specific texture, you are sending a continuous, non-visual tactile signal straight to your somatosensory cortex and your hippocampus. This physical anchor acts as a constant reference point, allowing your brain to maintain a baseline map of physical reality, even while your visual cortex is entirely consumed by the virtual world. This drastically reduces sensory conflict, mitigates spatial disorientation, and dramatically cuts down on the severity of virtual reality sickness. Second, you must manage your gaze transitions to prevent cognitive drift. When you are inside a virtual environment, avoid rapid, unnatural head movements that run ahead of the display's refresh rate. Instead, practice moving your eyes first, allowing your gaze to lead your physical head turns, just as you do in physical reality. When you decide to end your session, do not simply rip the headset off your face in a bright room. Instead, close your eyes, gently remove the device, and keep your eyes closed for 20 to 30 seconds in the physical environment. This quiet pause allows your visual system to reset its exposure levels and gives your vestibular system a moment to re-register the steady pull of gravity before you force your eyes to align with physical space again. Third, establish a post-session physical integration routine. After you step out of a virtual environment, spend exactly 5 minutes engaging in sensory-rich physical activities. Walk around your room barefoot, squeeze a tennis ball, or gently stretch your arms and legs. This is not just about physical stretching, it is a neurological calibration phase. By actively engaging your muscles, joints, and skin in the physical world, you are sending a flood of proprioceptive data back to your hippocampus. You are telling your brain's place cells, "We are back." The physical laws of gravity and friction apply once more, and you can safely rebuild our standard spatial map. This rapid recalibration prevents the sluggishness and spatial dissociation that many people feel for hours after using immersive displays. When you look at your screens now, you will no longer see them as simple windows displaying images. You will see them for what they truly are: sensory intervention systems that are actively negotiating with your nervous system for control of your perception. Your relationship with technology is not just psychological, it is deeply biological. Every interface design choice, every frame rate, and every simulated light source is a direct physical intervention into the neural pathways of your brain. You are the custodian of an incredibly sophisticated, highly plastic biological masterpiece. When you step into virtual space, you are not leaving your biology behind, you are taking it on a journey into a terrain it was never originally designed to navigate. By understanding the deep science of how your brain maps the world, you can explore these digital dimensions with absolute confidence, keeping your mind sharp, your senses aligned, and your physical self beautifully grounded. Now that you understand how virtual light and spatial mapping are actively reshaping your brain's physical GPS, the next step is to look at how we are altering our internal sense of time and rhythm. There is an invisible, silent biological clock ticking inside your auditory system, and the modern devices we wear on our ears are changing its frequency in ways that scientists are only just beginning to decode. Until next time, keep decoding your digital world, understand the biology of your daily habits, and stay brilliant.